Hello everyone, my name is Dan the Tutor. Thank you all for joining me to the Physics 202 Exam 1 review session, Fall 2023. This is going to be very similar to the one I had last year and last semester. You will notice there's a couple differences. Of course, unless you're repeating the grade, you wouldn't even know what changed from last semester to this one. But regardless, we have about 30 questions to go over today about waves, frequency, Doppler effect, constructive and destructive interference, electric forces, electric fields, electric potential energy, Gauss's law, and anything else I'm forgetting, we're going to see it right here. There was one thing I was going to say. Oh, it's going to kill me if I don't remember. Okay, well, if I think of it, I'll say it. But regardless, we're going to get started today. Basically, if I write something down, it means I think you should write it down too. And if I didn't give enough room to write the thing down, well, I apologize. Hopefully you can write in the margins. Or if you have a scrap piece of paper, you can do that too. You do not need a calculator tonight. All the calculations have basically already been done for us. In other words, I did all the calculations on the calculator ahead of time. So that obviously will not be done for you on the exam. But for right now, it doesn't matter. Okay, so we're going to get started with waves, frequency, and wavelength. First, we have the types of waves. So the two types of waves that there are, you have longitudinal, and I hope I'm spelling this right, longitudinal waves, and you have transverse waves. And if you remember, longitudinal is the ones that go up and down. I'm sorry, I have that backwards. Transverse is the one that goes up and down, looks like a sine wave. And longitudinal is like sound waves where there's clusters and they get close together and then they get more spread out apart and then they get close together again. That's what longitudinal looks like. An example in real life would be sound waves. An example of transverse waves would be literal waves in like the ocean. So these are the two kinds of waves. I don't think it's important to know anything beyond this. And now we have an equation for wave speed. This is probably the number one equation, not for the first exam, but certainly for waves. Number one equation. It's velocity equals lambda times f. Hopefully you know already that lambda is the wavelength and f is just the frequency. Lambda, the wavelength, has units of meters and frequency has units of hertz. Then we have frequency and period. Frequency is related to the period because frequency f is equal to 1 over t, where t is the period. And the difference is frequency is basically saying how many times per second does something happen, while the period is the opposite. It's how many seconds to complete one oscillation or wavelength. So any questions on anything I've said so far? Okay, next we have two constants that I don't think you have to have memorized, but I probably would if I were you. The first is the speed of light. That's c equals 3 times 10 to the 8th meters per second. Although this one isn't really used on the first exam, not nearly as much as speed of sound, which is v equals 343 meters per second. Now technically the speed of sound depends on the temperature outside, but assuming it's standard temperature, like just normal temperature, it's always 343. They would have to tell you in the problem if it's not. So we're going to always use 343 for speed of sound. Any questions so far? Okay, next. We have the very first question of the night. How exciting. You listen to a radio station FM 102.3, which has broadcast frequency 102.3 megahertz. The waves travel at the speed of light. What is the period of wavelength of those waves? So I'm sure the first thing, before you're even thinking about the question, you're probably thinking, is that really what the numbers on the radio mean? And the answer is yes. And the FM part stands for frequency modulation compared to AM radio, which is amplitude modulation. Now, you don't know what that means, nor should you. The only reason I learned it was because I took it for electrical engineering, and even today I could not tell you what that means, so it doesn't matter. What does matter is the fact that I give you a frequency of 102.3 megahertz, and you better believe I do have to convert that back to my base unit of hertz. Mega is a weird one. We usually don't see this in physics, but if you do, mega simply means 10 to the 6th power. I'm going to just take a second to write all the conversions you're going to need today. Mega is 10 to the 6th. The other common one is micro, which is 10 to the negative 6. Then you have nano, which is 10 to the minus 9th. And then milli, which usually just means divide by 1,000. You can also write that as 10 to the minus 3rd. And so these are all the conversion factors we're going to need for today. I recommend memorizing all of them because they're very important. So now I'm asked to find the period and the wavelength. And I gave us the frequency, which is 102.3 mega, so times 10 to the 6th, hertz. And if I want to find the period, period's easy. Period is 1 over the frequency, so 1 divided by 102.3 times 10 to the 6th. I know I said a minute ago that, if I just scroll up slightly, I said that frequency equals 1 over period. Well, if you solve for t equals 1 over f, so here we go. And if you plug this in a calculator, you'll get a period of 9.78 times 10 to the negative 9th seconds. So pretty safe to say, very fast, because it's taking place in a nanosecond, basically. We can't even see that with our naked eye. And then next we need to find the wavelength. To find the wavelength, I'm going to be using this fact, V equals lambda times F. In this case, you probably don't know this yet, but radio waves travel at the speed of light. And again, that's more of like a second exam topic. So I'm just going to tell you this, and they'd probably tell you on the exam, radio waves travel at the speed of light. But either way, now you know. So in other words, 3 times 10 to the 8th, the velocity, is equal to the wavelength, which I'm solving for, times the frequency. 102.3 times 10 to the 6th. And yeah, so this lambda, if I want to solve for lambda, I just divide both sides by the frequency, 102.3 times 10 to the 6th, and I get 2.93 meters. And this is our answer. So in other words, in case you're curious, 2.93 meters, that's pretty big. That's about 3 yards, okay? In other words, if radio waves were visible, which they're not, we can't see them, but if they were visible, they would be pretty long. Like that, we would definitely be able to see them in real life if we could. However, one thing you notice, radio waves are some of the biggest waves compared to other waves such as ultraviolet, visible light, gamma rays. Again, I'm getting ahead of myself. This is like second exam stuff I'm talking about. But I'm just telling you now because it's all related and I just geek out about this stuff. And so that's it for the first one. Lambda was 2.93. The period was 9.78 times 10 to the negative 9. Any questions on the first one? Okay, next, number 2. You drop a rock down a well and wait to hear the echo. If the well is 30 meters deep, how long will it take to hear the echo? So for this problem, you just need to realize that this problem is 2 parts. So first, here's my person. They drop a rock down a well. The well is 30 meters deep, and we're dropping it. So in other words, initial velocity is 0. V initial is 0. The reason why this is 2 parts is because the first part, the rock is going to drop, hit the bottom. The second part is we got to wait for the sound to travel back up. So then for the first part of this problem, I'm just going to write for the kinematics part. This is kinematics. We have an object falling. This will be physics 1. So that means what I do for kinematics is I write V initial, V final, acceleration, time, and displacement delta y. Then I ask myself, what do I know? So V initial is 0. V final is, we don't know that. Acceleration is negative 9.8 because it's always negative 9.8 for acceleration. The time is what we're solving for, and delta y is 30. And if you write 30, you're wrong because it's negative 30. It's going down. You got to write negative 30. So now we got to plug into a kinematic equation that has 3 of these 5 variables in it, and time, of course. You're going to have an equation sheet on the test, so I'm sure that the kinematic equations will be there. But since I have them memorized, because I also tutor Physics 1, I will tell you it's delta y equals V initial times time plus 1/2 at squared. Which then begs the question, should I have that memorized, or should I just know how to do it? And how much of Physics 1 do I need to know for this exam? Because one thing I noticed in the homework recently is that there's a lot of Physics 1 topics. There's a lot of force questions that showed up. There's a lot of centripetal force and centripetal motion that showed up. And my answer to you is basically, if it shows up on the homework or it shows up in lecture, then it's fair game for the exam. And since we've now seen kinematics with waves, we saw centripetal motion and forces tied in with electric fields and electric forces, I will tell you it's fair game, and you ought to know how to do that. And I don't have a ton of questions involving those topics just because it's not that important. What's more important is the Physics 2 topics, like the new ones, so I'm spending the majority of the time today talking about those things. But you will notice I will throw in a Physics 1 topic, just like I am now with this problem. So delta y is negative 30, v initial is 0, time is whatever, plus 1/2 negative 9.8 times t squared. If I simplify this, I get negative 30 equals negative 4.9 t squared. I just simplified, combined like terms. Then I'm going to have to divide both sides by negative 4.9. And when I do that, I have positive 6.12 equals t squared. And then I just got to take the square root of that. Remember, whenever you take the square root, it's plus or minus. But you can't have a negative time, so don't even worry about it. I just like to get you in the habit of thinking of it because other problems, it does matter with the plus or minus when you take a square root. So anyways, the final time is 2.47 seconds. And that's our answer. Again, we forgot something. This is just the kinematics part. This is the time it takes for the ball to hit the ground. We still got to calculate the time to hear the echo. So in other words, I can call this time t1. Sure, it's most of the time. It's the majority of the answer. But we still got to use sound and sound velocity to find the speed and the time it takes to come back up the well. To do that, we basically just use one equation, velocity equals distance over time. We use this equation whenever you want to see sound traveling a distance. The reason why we use this actually is because this is constant speed. In other words, the speed of sound is a constant. It's not going to speed up or slow down. It's always 343. So that means the velocity, 343, equals the distance, 30. Don't put negative 30 for that distance because then you'd get a negative time and that wouldn't make any sense. So in other words, only worry about the distance being negative for kinematics. This doesn't matter. And then divide it by time. To solve for time, I multiply both sides by t, and then I divide both sides by 343. So t equals 30 divided by 343, and I will get a time of 0.09 seconds. And again, that's like t2. That's like the second time. To find the total time, I got to add my two answers together. So 2.47 plus 0.09, I get a final answer of 2.56 seconds. Any questions on that one? Anyone still writing? Okay, great. Next, we go on to our next topic, which is standing waves. When we talk about standing waves, this is like the both ends open, both ends closed stuff. And maybe you didn't understand it at the time, but let me just lay it out for you as simply as I can. First, the both ends closed case. This is like a guitar or a violin or any stringed instrument. And basically, if I were to draw a picture of this, it would look like this. Where if it's fixed on both ends, it looks like this. And today I'm going to draw the second harmonic for you guys. This is the second harmonic, n equals 2. Because to count the harmonic number, you just count the number of loops. In other words, there's one loop there, there's one loop there. Total of 2, that's why it's n equals 2. And by the way, you can do the same thing for the both ends open case as well. You can just count the number of loops, but it's a little harder. We'll talk about that. And then the equation that we're going to use for the both ends closed case is L, the length of your thing, is equal to n, the harmonic number, times wavelength lambda, divided by 2. And of course, don't forget this equation, which we'll be using all day today, V equals lambda times F. So I know I just said a lot. Any questions so far? Okay, good. Next, we have the both ends open. This is like any woodwind instrument. I'll put a flute as our example. You imagine it just as air passing through holes in a pipe. And so for that reason, the diagram will look something like this. This time I'll just draw the first harmonic, which looks like this. This is n equals 1. The reason why is because if you count the number of loops, there's 1/2 loop over here and 1/2 loop over there to make a total of 1 loop. And that's why it's n equals 1. And by the way, L equals n lambda over 2. It is literally the same equation that we had for both ends closed. So both ends open and both ends closed are extremely similar to each other. And as we'll find out in 1 second, the last case, the one end open, one end closed, this is like the problem child. It's very different. So for the one end open, one end closed, the most similar example in real life is a bottle, like literally like a plastic bottle, like the one you see on my screen. Or if you're watching the recording, just imagine a beer bottle. So then what this is going to look like is first I'm going to draw one end open, one end closed. And today for you, I'm going to draw what the third harmonic looks like, which looks like this. This is the third harmonic, n equals 3. The reason why is because for the one end open, one end closed, you got to count the half loops. I count the half loops. So in other words, if I cut this in half, that's 1/2 loop, there's 2 half loops, there's 3 half loops. That's why it's n equals 3. And the equation is also different. The equation is L equals n lambda over 4. N lambda over 4 for the one end open, one end closed. Furthermore, one last thing I'll say is n has to be an odd integer. In other words, 1, 3, 5, 7, etc. has to be an odd integer. It just doesn't work with even numbers. And you don't really need to know why, you just have to take my word for it. But are there any questions on anything I've just said? Okay, good. And then the last thing, waves on a string, just a very simple equation. The wave speed, and by the way, this is if you have like a physical string, like you go to the gym and you see the people doing the rope thing up and down. Perfect example of this. The wave speed V is equal to the square root of the tension force Ft divided by the linear mass density mu. So let me write that out for you guys. Ft is just the tension force. And Greek letter mu, known as the linear mass density, one of the worst sounding variables ever. Linear mass density is a very simple equation. It's just the mass over the length. Sometimes they tell you what the linear mass density is. Other times they give you the mass and the length, and you have to calculate it. God forbid. Any questions before we go to the example problem? Okay. So then number 3. A person strums a guitar at its fundamental frequency. By the way, fundamental frequency, you should know what this word means. It means n equals 1. That's immediately what I'm going to write for fundamental frequency. The length of the string is 75 centimeters, so that means L equals, I'm not writing 75, I'm converting to meters, so 0.75 meters. And I want to find the wavelength first, and then it says if the string has a mass of 5 grams and a tension of 68 newtons, I want to know the frequency too. Okay, so the first thing we need to figure out, guitar, which case is that? Obviously we know it's the both ends closed case, because that was our example for the both ends closed case, which means that the equation is L equals n lambda over 2. We have the length, it's 0.75. We have n, it's 1. So then to solve for lambda, you just have to multiply both sides by 2. And you'll get lambda equals 1.5 meters. And there's our wavelength. And so now the second question asked, what is the frequency of the tone produced? If we want to know the frequency, then we got to use this equation. V equals lambda times F. And then we're solving for F. So the good news is we know wavelength, 1.5, but we don't know the velocity. And by the way, it is not 343. The only time you can assume it's 343 is if the sound is traveling through air. And you may be thinking, well, isn't the sound of a guitar traveling through air? And, well, I guess technically yes. but we're talking about the guitar string itself, okay? So the guitar string is not moving at the speed of light. The sound is traveling at the speed of light. Very important distinction there. So then v equals lambda times f. We need to find the velocity, and luckily we have an equation to do that. It's the physical string equation, v equals square root of ft over mu. So first I'm going to find mu, the linear mass density. That's not too bad because they gave me a mass of 5 grams. Of course I'm not going to write 5. I need to write 0.005 because I have to divide 5 grams by 1,000. So 0.005. And then that's divided by the length, which is 0.75 meters. And then I plug that in the calculator and we'll get 0.0067 for our linear mass density. So that means V equals the square root of the tension force, which they tell us is 68. Great. And then divided by the linear mass density, 0.0067. Perfect. You plug this in a calculator, you'll get a velocity of 101 meters per second, approximately. And once you have the speed and we have the wavelength, you can easily find the frequency by plugging back into our wave speed equation. Divide both sides by 1.5. We get a final answer of frequency equals 67.3 hertz. 67.3. Any questions on that one? Good? Anyone still writing? Great. Okay, next we have number 4. You want the third harmonic of a standing wave to be 400 hertz. Assuming all the wave speeds are identical, which shape will produce this with the shortest length? Both ends closed, both ends open, or one end open and one end closed? Great question, a real good conceptual question. By the way, one thing I tried to do this time around that, I've been doing these exam reviews for basically since 2020, and one thing I can tell you is I never ask that many conceptual questions because I personally like the math questions a lot more. Well, good news for you guys, and also bad news, this exam review has more conceptual questions than any exam review I've ever put together. I know. Yeah. So the good news, that's good and bad, because the good news is it's going to be faster because there's less intense math we're going to be doing today. It's also worse because I don't think anyone loves conceptual questions. Kind of roll your eyes. But the good news is the way I solve conceptual questions is the exact same way I solve normal questions, calculation questions. And that is by using the formula and plugging in numbers. So for this one, we want the third harmonic. In other words, we immediately know n equals 3. We also know the frequency is 400 hertz. And now we got to calculate the shortest length. So in other words, we're solving for the length L for all 3 cases. So what would be easy to do for this one is basically, let's start with the both ends closed. It doesn't matter which we start with. We have to start with one. So we'll start with both ends closed, and I'm going to write the length equation for this, which is L equals n lambda over 2. Actually, we know what n is. N is 3, so L equals 3 lambda over 2. And now we got to find lambda by using the wave speed equation. This is the part that sucks about conceptual questions, is that sometimes there's unknown variables, and the unknown variable today is velocity. We don't know the velocity. Now, can you assume it's 343? You actually can. It's not technically right because you don't know the wave speed because it doesn't really say it in the problem. But if you do use 343, it doesn't matter. As it turns out, the velocity doesn't matter at all, or else I would have told you. And by the way, if the problem does not tell you and you wonder, is it okay to assume it's 343, the speed of sound? Then I would say yes, that's fine. If you have no idea, worst case scenario, just put 343 for the speed. You'll probably get the right answer. And if not, you would have got it wrong anyway, so at least you gave yourself a fighting chance, right? So anyways, I'm going to actually leave it as v to prove that the velocity doesn't matter. Lambda is what I'm solving for, and the frequency is 400. So in other words, if I want to solve for lambda, just divide both sides by 400. Lambda equals v over 400. And so then if I plug that into my length right here, I'm going to go on a different page because I'm running out of room. I'm going to get L equals 3 times V over 400 divided by 2. Now this looks pretty ugly, that's because it is. But the good news is I can easily just have, for the numerator, I can have 3V. And in the denominator, I can just multiply 402 and I get 800. So L equals 3V over 800. Any questions so far? I know I don't know what the velocity is, but it doesn't matter because I'm just comparing the three different results between both ends open, both ends closed, and one end open, one end closed. Okay. So the next, what I'm going to do is we're going to do the both ends open example. For both ends open, it's going to be L equals N lambda over 2 again. And actually, since it's the exact same numbers, in other words, when you do V equals lambda F and the frequency is 400, you get the same value for lambda. It's the exact same numbers. In other words, the result is going to be the same. L equals 3V over 800. And if you actually do the math, you would see that. Any questions so far? Okay. And then the last one is the one end open, one end closed. One end open. And for this, L equals N lambda over 4. Don't forget, it's over 4 now because that's what the equation is for one end open. And also, the wavelength is honestly still the same. It's still V over 400. The wave speed does not change with a bottle example. The wave speed does not change. So still V over 400. Which means when I plug this in, I'm going to get L equals N, which is 3. And 3 is okay because it's an odd number. If it was an even number, it couldn't be one end open, one end closed. It would just be automatically not it. But N is 3. Wavelength is V over 400. And then divided by 4. This gives us an answer of L equals V over, 3V over 1600. Let's compare that to the answer we just got a minute ago. 3V over 800. Remember, we wanted the shortest length. So who's the shortest length? If you don't know, you can plug it in your calculator. It's definitely going to be this one. The one end open, one end closed. That has the shortest length. And again, I've just proved that the velocity doesn't matter because V shows up in both equations. You can think of it as the velocity canceling out. Any questions on that one? Okay, good. Then we're on to number 5. And I think this is the last one for these standing waves, so nice. The picture below shows a standing wave pattern for an organ. If the frequency is 1.5 kilohertz, what is the wave speed? So you'll notice we're solving for the wave speed this time. That means you probably shouldn't say it's 343 or else we'd be done the problem immediately, right? So instead we're going to use our favorite equation. V equals lambda times F. Now we don't know the wavelength. We actually do know the frequency. It's 1.5 kilohertz. Remember, kilo means 1,000, so 1.5 times 1,000 is 1,500. That's the frequency in hertz. But now we got to find the wavelength. And so to find the wavelength, I'm going to say L equals N lambda over 2. This is the pipe organ. You clearly see it's both ends open in this example. And I need someone to tell me what the harmonic number is, because I'm not going to say it.
Is it 3?
It is 3, thank you. And that's because we have one loop here, a second loop here, and then 2 half loops that make a full loop, and is 3, yes. We also know the length is 4 meters, which means that 4 is equal to 3 times wavelength, which I'm solving for, divided by 2. So to solve for lambda, I first multiply both sides by 2. 8 equals 3 lambda. And then I divide by 3. Lambda is going to equal 2.667 meters. And of course, that's not the final answer, because I still need to plug it into this equation. V equals lambda times the frequency. So that means V equals 2.667 times the frequency, which we said was 1,500. And that's going to give me a final speed of about 4,000 meters per second. You'll notice considerably higher than 343. Is there a reason for that? I don't know, but it's a good practice problem, so you don't have to think too critically about that. Any questions? Nope. Okay, great. Now we're on to the next topic. Decibels and intensity. So first, I need to give you the equations for converting between the two. If I give you I and you need to go to dB, decibels, then what we would say is decibels is equal to 10 times the log. And remember, if I say log, that's log base 10, or honestly just the log button on your calculator, not natural log. It's the log of I over I naught, where I naught is equal to 10 to the minus 12th power. This is known as the threshold of hearing. In other words, if it was any quieter than this number, then you would not hear a thing. Okay, so that's it for that equation. Now we need to talk about what to do if I give you decibels and you got to convert back to the intensity. And that equation looks like this. I, the intensity, is equal to 10 to the power of decibels divided by 10 times I naught. Or again, I naught is 10 to the minus 12th. And the one note I'm going to tell you that's going to help you solve these problems is you can only add sounds in intensity, not decibels. You can only add sounds in intensity, not decibels. And by the way, there is an exception to that rule, and I'll cover the exception after we do example 6. So with that, let's go to example 6. When two friends talk, their total intensity level is 65 decibels. What would be their total intensity level in decibels if 5 friends were in the room, assuming they all talk at the same volume? So what many of you probably did when you first started learning about decibels and intensity, you probably just multiplied this answer by 5, and you would get an answer of 325, which, to put this in perspective, if this really was the answer, then your ears would literally blow up. This is louder than standing next to a rocket taking off. So don't do that. Then what do we do? I mean, probably some of you remember what I said if I met with you in person, or even if you just learned now this is how you do these problems. The first thing you got to do is you got to convert decibels to intensity, and that's because we can actually add the intensities together. We can't do that with decibels. We're just not allowed. So then, if I want to convert to intensity, I would say I equals 10 to the power of 65 over 10 times I naught, which is 10 to the minus 12th. And so if I plug this in my calculator, and assuming I plug it in right, which of course I would, why would I ever not? I would get 3.16 times 10 to the minus 6th, and I have no idea what the units are. It really doesn't matter. But again, this is the intensity for 2 friends. So if I want to find the intensity for 5 friends, here's what I would do. First, take my intensity, 3.16 times 10 to the minus 6, divide it by your 2 friends, and that's going to give you an answer of 1.58 times 10 to the minus 6. And now you have the intensity for 1 friend. And that's great, because then if you have 5 friends, now you just take this answer and multiply it by 5, because there's 5 of you, there's 5 friends. And you'll get a final answer of 7.91 times 10 to the minus 6 as your intensity. That's for 5 friends. And if you circle that, then you jump to the gun. It's not the final answer, because if you read the question, they want it in dBs. So now we got to convert our answer back to decibels. And we had to do it this way. We had to go to intensity first, then go back to decibels. There's no shortcut here, I promise. So here's what I'm going to say. If I want decibels, decibels is just equal to 10 log of our intensity. We just got 7.91 times 10 to the minus 6, divided by I naught, 10 to the minus 12. And if you plug this in a calculator, you get 69 decibels. Remember, our original decibels was 65 decibels, so that's only an increase of 4 decibels. not nearly close to 325, which was what some of you may have gotten. Any questions? Okay, anyone still writing? I hear someone's unmuted. Do you have a question? Nope. Okay. So, like I said, I would tell you the exception. And the exception is going to be if they ever say one sound is, like, let's say 3 more decibels. Like, if it's 3 more decibels, and they actually use this language, like they say decibels in the wording of the problem, that's the only time you're allowed to add it. So, in other words, it went from 65, it goes to 68 decibels, and then they'll probably ask you to convert back to intensity. Okay, fine. That's the only time you're allowed to add sounds in decibels if it literally says decibels, like you added 3 more decibels. Because notice, in this problem, I said the sound was 65 decibels, but we still had to convert to intensity first. And that's because I didn't say multiply the decibels by 5. I did not say that. And I never would. Sometimes you'll see plus decibels, you'll never see times decibels. You just don't do that. Any questions with that? Okay. Number 7 uses an equation that I have not given you yet. That is my fault. So the equation is I, the intensity, has actually a second equation. Intensity is defined as a power over an area. And since we live in a 3D world and the area is the surface area of a sphere, which sounds very familiar to Gauss's law, but either way, the area will always be 4 pi r squared. Always. Well, that's not true. One time it was pi r squared in the homework question, and I, to this day, don't understand why that happened. But in general, power over 4 pi r squared, that's going to be our intensity equation for a 3-dimensional world that we live in. So now we're going to read the question. You hear a car 100 feet away honk its horn with intensity I1. Another person hears the horn a distance of 300 feet away. If the new intensity is x times I1, what is x? So some of you may be thinking, hey, this sounds like a Doppler effect problem because, there's different distances and like you're hearing a car. And this is almost a Doppler effect problem, but the problem is I'm asking about intensity, which is fine. So one thing you're going to notice is that I have no idea what the power is. I don't have it in any equation, and the truth is it doesn't matter, so I don't even care. Here's how I'm going to solve this. The first thing I'm going to do is I'm going to find I1. And I1 is the power p, which I don't know, nor do I care, divided by 4 pi, and the radius is 100 feet, so 100 squared. Now you may be thinking, hey, don't I need that in meters? I can't use feet. And that's true for most problems. However, I don't think you can convert feet to meters, so even if you wanted to, you couldn't. And number 2, we don't need to do that because this is a comparison problem. We are comparing one scenario to another, and so as long as the units are the same, we're going to be fine. And again, the reason for that is it's a comparison problem. I'm also not going to plug this in a calculator because frankly, I just don't care. All I care about is this general form. And what I also care about is the difference. I repeat, all I care about is the difference. I don't care about the numbers really at all. So then when I go and calculate I2, I would say this. That's the worst 2 I've ever drawn. I2, there we go. I2 is the power, which did not change, divided by 4 pi. And watch this. Instead of saying 300 squared, I'm not going to say 300 squared to make you mad. Instead, I'm going to write 3 times 100 squared. And why would I write it like that? Because I'm recognizing that the difference is a factor of 3. Because that's what they're really asking about. Now, if I want to simplify this, I am going to square the 3, because technically I should square both the 3 and the 100. So in other words, I get p over 4 pi, 3 squared is 9, and 100 squared is still 100 squared. Now, why didn't I square the 100 again? Because again, we're just going to play a game of comparison, spot the difference. Here was my original I1, and basically I have the p here, I have the 4 pi here, and I have the 100 squared here. The only thing that's different is the 9. And it's in the denominator, so in other words, the answer, the factor, the change, whatever you want to call it, it's 1/9 I1. If I1 is everything in red, the p, the 4 pi, and the 100 squared, the only thing left over is a 1/9. In other words, if the new intensity is xi1, x is 1/9. There's multiple ways to solve this problem, but I certainly think this is the easiest. Any questions on number 7? Okay, great. It either means I'm doing a really good job explaining or you people are shy. Either way, I don't care. Less questions for me to answer. Oh, I finally remembered what I was going to say. Better late than never. So this is obviously a free exam review, which is why you didn't pay, obviously, to get in here. Just so you know, everyone after this will cost money. It will, I think, be $50 for the whole thing. I forget exactly what my price point is. But regardless, I think you would agree that you're getting a lot more than $50 worth here because you're actually learning, well, basically everything in 3 hours. It's like you don't even have to show up to lecture. You can just watch this. Of course, I don't recommend doing that. That would be idiotic. But you could, theoretically. And so now we're on to Doppler effect. So Doppler effect has the following equation. I probably do it slightly differently than your professor, and that's because my way makes sense, implying your professor's way doesn't, and we all know that. So anyways, the frequency O equals frequency S times parentheses fraction bar. In the numerator, I have V plus or minus VO, and in the denominator, I have V minus plus VS. And now I need to explain what all these variables mean, which I will. So whenever you see the letter O just means the observer, the person who's hearing the sound. Whenever I say S, I'm talking about the source. In other words, like the person making the sound, or sometimes it's like a vehicle or like an animal or whatever. And then just V, when I say like just V, like this V here and this V here, these V's are 343 meters per second. That's if we're talking about the speed of sound. Of course, it depends on the problem, but 99% of the time it's the speed of sound in air. And the reason I say in air is because if it's speed of sound in water, it's like 4 times that or something like that. But I think they'll tell you in the problem, I hope. So the last thing is, we need to talk about the plus and the minus plus. What the heck does that mean? So for those of you, again, who have met with me, at least you should know what I'm going to say. I'm going to say use the tops. And when I say the tops, I'm talking about this one and this one. We're going to use the tops when you're going for toward, like you're moving toward the object, or the object's heading towards you. That looks like it says toys. I just want to be clear, that's a P. It says tops. And then you're going to use the bottoms, in other words, the bottoms, okay, if you have away, like the objects are heading away. Now, I want someone to tell me, true or false, it's possible to use the top for the top equation and the bottom for the denominator. In other words, plus both times. Is that possible, or would that never happen? Any ideas?
Is it possible because the bottom is like for the source and the top is for the observer?
So you're saying if the source is heading away from you, like a car driving away, but you, the observer, are heading towards it, like you chasing after an ice cream truck, then yes, that would be a good example. So it certainly is possible. In other words, you need to think about it. And what better way of thinking about it than the first example we have with number 8. A cat is chasing after a mouse. The normal frequency of a cat's meow is 800 hertz. The mouse hears a frequency of 758 hertz. Will the cat catch the mouse? A great conceptual question. Who thinks they've got it? I want to give you a hint. You really don't need the equation because, well, normally you need the equation, but there's a shortcut with the equation you ought to know. And that is, if you hear a higher frequency, then is the object getting closer to you or farther from you? Does anyone know? If you hear a higher frequency...
Closer.
Yes, it's getting closer. So if you hear a higher frequency than normal, it's getting closer. Similarly, if you hear a lower frequency, then obviously it's getting farther. the distance between you is increasing. And if it's the same frequency, then you're moving at the same speed, so we probably won't see that example on the test. But now we know the cat's meow is 800 hertz, the mouse hears a frequency of 758. The question is the cat getting closer to the mouse or farther from the mouse? And the answer is farther from the mouse, because you're hearing a lower frequency. That means they're getting further away, and because of that, the cat will not catch the mouse. No, they're getting further away. Okay, anyone still writing? Good. Now, by the way, for most conceptual questions, I do recommend actually writing the equation. This one I don't, only because you can just know this shortcut. This is one of the few shortcuts I recommend knowing. Number 9, you cannot use a shortcut for. Well, that's kind of a lie, actually. But we'll talk about it. Number 9, a train blows its whistle as it heads into a tunnel. It's traveling at a constant speed of 55 meters per second. If the train's whistle had a frequency of 1200 hertz, what should be the frequency of the echo from the tunnel? Great question. So the secret to this one, well, before I get to the secret, let's just set up the scenario. Let's draw a picture. I've got a train heading into a tunnel with a speed of 55 meters per second. Now the frequency going out is 1200 hertz, and it's basically going to bounce off the cave walls and come back, and we're going to hear a frequency. We'll call it frequency observer. That's kind of what we're solving for. And the question is, how do we do this? So here's what I'm going to say. The secret for me is that you split this up whenever you have an echo problem. Whenever you have an echo problem, split it up into 2 parts. First, before the echo. So before the echo, this is my source, it's the train, and the observer, the first observer is the actual cave wall, okay? Hopefully everyone sees that. And I know this sounds weird, but in a minute, the cave is actually going to become the source. The echo becomes the source, and so that's the secret to this problem. But before the echo, I set up the equation. Frequency of the observer, the cave wall, or tunnel, I guess, whatever, is equal to frequency of the source, 1200, times V, which is 343, plus or minus, I'll figure that out later, VO, the observer. Remember, the observer is the cave wall, or the tunnel wall. That is not moving. The wall is not moving. That's 0. And again, that's because it's the tunnel not moving. And then divide it by 343 minus plus the speed of the source, which is 55, and that is obviously the train. So now I need to figure out if it's plus or minus, in other words, the top or the bottom. Obviously, for the tunnel part, it doesn't matter. That's just 0, plus or minus. I don't really care. It's not moving. But who can tell me what the train will be? Will that be minus or plus? It's getting closer or further? It is going to be getting closer to the cave, basically. So for that reason, we use minus. We use the top because it's getting closer. Train's getting closer to the wall. So then that means the math will become 1200 times 343 over 343 minus 55. And again, I did this earlier on my calculator. We get 1429 hertz. Like I said, this is half the problem, okay? Because this is before the echo. Now for the second part of the problem, the echo becomes the source and the train becomes the observer. Hopefully that makes sense to everyone. And by the way, you can do the same formula we just did. You got to think of the variables because some of them changed. Or you can use a shortcut that, again, I don't like shortcuts, but this one works for whenever you have an echo problem. The shortcut for the echo problem is that all you have to do is double the change in frequency. Double the change in frequency. So what does that mean? Well, the first answer I got was 1429 hertz. And if I want to find the change, I'm going to subtract it from the original 1200. So in other words, I get 229 hertz. That was the change in frequency for the cave. And now what I'm saying is, because this is a symmetrical case, because the, train's going one way, bounces off, coming back, everything's symmetrical here. So you just have to double the change, times 2. You're going to get 458 hertz. And you just have to add that to the original number, which was 1200. In other words, 1200 plus 458 gives you 1658 hertz. And that's the final answer heard back by the train. And I like that shortcut because it's pretty nifty. Any questions on number 9? Anyone still writing? Okay, good. Then next, we're almost to, basically the meat and potatoes of today, and what all of you are excited for, is for the electricity part with the electric force, the electric field. This is the last topic before we get there. It is constructive and destructive interference, and we're about an hour in, so I would say, are right on track of where we should be. So I'm very happy right now. So constructive and destructive interference, one of the topics I used to hate the most because I had no idea how to do it. But now that I know the equation and how to solve these problems, I realize they're really not that bad and they're actually kind of nice. So here's what I'm going to write for the interference equation. By the way, I do this for both constructive and destructive. I write the absolute value of d1 minus d2 equals m times lambda. Your textbook will do something different, by the way. Your textbook will give you this equation for constructive, and for destructive, they'll give you m plus 1/2 lambda. Don't write that down because I'm not going to do that. I don't like doing it that way. I think it's confusing. So what I do instead is I say for constructive interference, I say that m is going to be all the whole numbers, 0, 1, 2, 3, ... And then if you want destructive interference, then just do m as the 0.5 values. For instance, 0.5, 1.5, 2.5, etc. That's how I solve these problems, and it makes my life a heck of a lot easier. And one thing you should know is that since there's infinitely many answers for what m can be, that means there's infinitely many answers to what the answer could be. The reason that's actually not true is because most of the time, the question is going to ask for like the minimum distance or the maximum wavelength or something along those lines, implying that we need to use the smallest m value possible. Use m equals 1 for constructive, use m equals 0.5 for destructive, and that's a good rule of thumb to do always. By the way, you may be thinking, why not m equals 0? 0 is a special case. It's a really weird, it rarely ever happens. But you would only use m equals 0 if d1 equals d2 exactly. And since that would be like a non-solution, in other words, if you plug in m equals 0, you're not going to find wavelength. It's just 0. Everything's 0. You can't solve anything with 0, so most likely the problem wants you to do 1. I say most likely because there's always exceptions to the rule. And then the last thing I want to say is sometimes you have speakers that are out of phase. If the speakers, that spells speakers, just to be clear. If the speakers are out of phase, and they will literally use that phraseology, out of phase, then switch constructive and destructive. But that's only if you see the word out of phase. Most of the time you don't. I hope you don't on the exam. And that's going to do it for interference. And now we're just going to do 2 practice problems and then move on. So anyone still writing? Okay, good. Next we have number 10. Number 10, 2 speakers are in a line on the x-axis. One speaker is positioned at -2 and the other is positioned at +2. If you are standing somewhere on the y-axis, what kind of interference can you experience? Constructive, destructive, or both? A great conceptual question. So I'm going to let you think about this for a second, but first, let me just draw the coordinate axis, okay? Here's X, here's Y. One speaker is at -2, the other speaker is at +2, and you're standing somewhere on the Y-axis. Since I don't say where, you can assume it's anywhere. Like, for instance, I can choose this point right here. Does not matter. Now, I just want you all to think about this for, just take a couple seconds. Can you have constructive, destructive, or both? And of course, think about the equation. The equation is absolute value of d1 minus d2 equals m lambda. I'll give you 30 seconds to think about it. Okay, time's up. Does anyone have an answer? Constructive, destructive, or both? No answers. That's okay. So, first, I'm going to call this distance d1. It's the distance from one speaker to my point. I'm going to call this distance d2. It's the distance from that speaker to my point. And if you think about it, this is kind of like a right triangle, which is absolutely what you should be thinking about right now. It's a right triangle. Both of these sides are 2 and 2 here, and they share the same height. In other words, you should notice that d1 must equal d2. d1 equals d2, and remember what I said when that happens. When you plug this in, you're going to get d1 minus d2, and since they're equal to each other, you just get 0. Which, remember, that means that m equals 0. And if m is 0, then that means it's constructive. And unless the speakers are out of phase, which I didn't say that anywhere in the problem, it can't be destructive. It can only be constructive. So no matter where you stand on the y-axis, looks like d1 will always equal d2, and you should always have constructive interference. Any questions?
Can you explain what is constructive and
Yes, absolutely. So basically, the easiest way I can describe this is with sound. Constructive interference sounds louder than normal, like you put two speakers together and it sounds louder. And then destructive interference is when it sounds quieter. And you may be thinking, well, that doesn't make any sense because whenever I have two speakers, it always sounds louder. And that's because the speakers are always in phase. In other words, your speakers, wherever you have them, are always, outputting at the same frequency and at the same time. But there's also these things called noise-canceling headphones, which basically can hear the sound coming in, put out its own signal to try and, counteract that. And what it does is it actually makes it destructive. You don't hear anything, or at least the sound is diminished. Does that make sense?
Yeah, thank you.
Great. Any other questions? Okay. Next we have number 11. Number 11 is another tough one. You are standing exactly halfway between two speakers. Both speakers are outputting at a frequency of 600 hertz. How far do you have to walk toward one of the speakers in order to experience destructive interference? Sounds very similar to a homework question I'm sure you had. It's because I based it on one. But if I have speaker 1 here, and you're standing, I think it's at exactly in the middle. Yep, exactly halfway. And then here's speaker 2. But it doesn't say the distance. So you know what I'm going to do? I'm going to make up my own distance, which you can do, absolutely. I'm going to say this is 10 meters. In other words, this distance is 5 meters. And obviously the other distance is 5 meters. And now it says I'm walking towards one of the speakers. It doesn't matter which one. I'll just say I'm walking towards speaker 2. It doesn't matter. But this distance, I'm going to call x. It's my variable. It's what I'm solving for. It's the distance that I'm walking towards speaker 2. Now, how far do I have to walk to get destructive interference? Well, for that, I'm going to set up my equation. And a lot of people don't even know where to start with this after I draw the picture, which I think is funny because there's literally only one equation for interference. So if you don't know what to do, at least start with this equation. Like, you can get the rest wrong, but at least start with this because it's literally the only logical thing to do. Okay, so one thing I'm going to tell you, you don't have to do this, but this is more of a conceptual, again, another conceptual question. When I was standing exactly in the middle, D1 was 5, D2 was 5, I was getting 0 for M, in other words, constructive interference. But now I want destructive interference. In other words, m equals 0.5. And I'm using the lowest value because, if I walk to 1.5, that means I already passed 0.5, and I don't want to pass 0.5. 0.5 is the first place for destructive interference. That's the one I want. So now it becomes kind of like an SAT question, because you have to figure out what D1 is. I'm going to give you a hint, because we're standing here now. I'm going to change colors just so it's different. We're standing here now at this red dot, which means this distance is my D1 and this distance is my D2. Can someone tell me what D1 is? And not like a number. Like if you say 3, for instance, I'm going to say no, it's not a number. It's like an expression.
Would it be 10 minus D1? Or 10 minus D2, I mean?
You mean 10 minus D2?
Yeah.
Okay, yeah, you can do that. I'm going to do just something slightly different because I define my variable x. So in other words, I'm going to say D1 equals 5 plus x. But technically, you can do 10 minus D2, and that would work as well. And then what would D2 be, also using x? That is going to be 5 minus x. Because you're going 5 and then you're subtracting x. And so now, I'm just going to plug into my formula. So that means absolute value of D1 minus D2, that's going to be 5 plus x minus the quantity, 5 minus x. Can't forget the absolute value. And let's see, that's going to be absolute value of 5 plus x. I'm distributing the minus, so minus 5 and then plus x. So it looks like the 5's cancel, and I just get 2x, which I guess I don't need the absolute value for because that's already positive. And that's the D1 minus D2. So now I just set that equal to m times lambda. So 2x equals m, which we already said was 0.5, and lambda, I don't have lambda. Does anyone know how we're going to find it? I'll go back to the other page. It is going to be our favorite equation, v equals lambda times f. Where I know I don't say what v is, but whenever I don't say what v is, we're going to assume 343, because the speed of sound. By the way, this makes sense in real life because, the sound is traveling through the air, and the air is traveling at 343. And again, if you don't know, use 343. That's a good rule of thumb. And then lambda, and then the frequency is, I think we said 600. Yes, we did. So then just divide both sides by 600. Lambda is going to be 0.572 meters. And once I have that, I can plug that in right there in my equation. So times 0.572. And then to solve for x, I just divide both sides by 2 and plug that all in my calculator. And I'll end up getting a final answer of x equals 0.14 meters. Any questions on that one?
Yeah, for the expressions that you did, why did you do like 5 plus x minus 5 minus x instead of just like doing the math with 0.5?
Right. So let me just go back. Here's a question. What would you call D1?
Like 5.5?
If that's the case, then you know x is 0.5. In other words, you're confusing the 0.5 from the destructive interference. You're confusing that with the actual distance x. And we don't know what x is, and that's why we had to leave it as a variable.
Okay.
Does that answer your question?
Yeah.
Okay. Any other questions? By the way, this was a lot better than the explanation I gave last semester. So you guys are lucky. If you want to know how I explained it last semester, I basically didn't do this, and I tried to work it through in my head just using logic. And it makes sense to me because I've been doing this for years, but my students had absolutely no clue what I was doing. So now I use the equation, and I think it went a lot better. So I'm very happy. Next, we have electric forces and electric fields. Yay! The meat and potatoes of what we're going to be doing today. So pay attention to this first page. This is going to be probably the most important page of the next hour. And you're going to mess up a lot of stuff, or at least hopefully you've already messed up a lot of stuff. And by that I mean you've done the homework, you've had lectures, and hopefully you know it better than you did 2 weeks ago. But I know this stuff is hard, and I know you're going to make mistakes, but just try and make the mistakes before the test. So that way on the test you've already made all the mistakes and you've learned from your mistakes. You know what I mean? Okay, enough of me blabbering. First we have the constants. The first constant we have is the charge of a proton/electron. And try and just leave room. There's only one more constant. But this is 1.6 times 10 to the negative 19. And the units are coulombs. By the way, protons are positive, electrons are negative. I'm not even going to write that. I think it's obvious. And then the only other constant we need right now is k, lowercase k, and that equals 9 times 10 to the 9th. And I have no idea what the units are for that, so I don't really care. But any questions on those constants? Hopefully they all look familiar. Okay, good. Next we have the electric force equation, Coulomb's law. And that is going to be Fe, or at least I call it Fe for electric, equals k fraction bar in the numerator, absolute value Q1, absolute value Q2 over the distance squared. I do two things different than the textbook. The first thing I do different is I use absolute values. The reason why I use absolute values is because I know the direction already for forces. I know that like charges repel, and I know that opposite charges attract. And so it makes no sense for me to include the signs positive and negative because it's just going to confuse me, and I hate being confused. And the other thing I do differently is the textbook likes to say r squared in the denominator, like a radius, but it's just a distance, and I like distance way more than radius, so I call it d instead of r, but it's the exact same thing. Any questions on that? Okay, good. Next, we have the electric field equation, and that is E equals K absolute value of Q over D squared. You'll notice something's different. It's missing a charge. So then that begs the question, which charge are we missing, Q1 or Q2? And of course, it's arbitrary. Like, why does it matter? So here's what I'm going to tell you. This charge right here is the charge creating. It's creating the E field. And so you get better at, with more practice, you get better and better at determining which charge that is. And then for the other equation, we actually have a second equation for electric field. That is E equals F over absolute value of Q. This is the other charge. This is the charge being affected. This is the charge being affected by the E field. It's also safe to say that you use the blue equation whenever you have force and electric field in the same problem. Because just look at these variables. Electric field, force, same problem. You should use that equation. Any questions on that? Okay. So then now we're going to talk about the electric field lines. This follows a very simple rule. For electric field lines, you're going to say away from positive and toward negative. That's the rule for electric field lines. The reason why this makes sense is because electric field lines describe the way a proton would move. I'll write that down right here. Electric fields describe the way a proton would move. And the reason this makes sense is because, well, think of it like this. If I draw a positive charge here, and we know that since it points away from positive charges, it's just going to look like this, away in every direction. So in other words, if I put a positive charge right here, it's going to want to go that way, in the same direction as the electric field line. And so that makes sense. And then if I have a negative charges do the exact opposite. Negative charges, everything points towards. And that's because protons want to go towards negative charges. So that makes sense. Any questions on that? Okay. And then hopefully you have some space at the bottom, because I just want to draw what the dipoles look like. What's a dipole? A dipole is if you have a positive and a negative charge close together, because then the electric field lines interact. They point away from the positive and towards the negative, and they're going to wrap around in just about every direction, like you see on my screen. And then if you have, like, let's say 2 positives, and something similar happens for 2 negatives, but electric field lines cannot cross. In other words, they veer off at the last second because they want to point away because they're both positive, but they can't. And the reason why they can't is because they cannot cross. Oh, that was a bad arrow, whatever. Good enough, you get the picture. So they just point away, but the ones in the middle kind of look funny. Any questions? Okay, then we're going to continue with number 12. Let me clear some space. Okay, number 12. 3 charges are in a line as shown in the figure. What is the net force on the leftmost charge? State the magnitude and direction separately. So hopefully you remember this. We have to use something called superposition. If you don't know what superposition is, it means it probably doesn't matter for you. But what it means to me is I am going to look at 2 pairs of charges at a time. In other words, if I'm focusing on the left charge right there, then the first thing I'm going to do is I'm going to do the 6 and the negative 9 nanocoulomb. And I'm going to find the force between those. And then I'll find the 6 and the 30 next. So first for that force electric equals K, which we know, times Q1, which is 6, but it's nano, and nano means 10 to the negative 9. And then times 9 times 10 to the negative 9. You'll notice I'm making it positive. That's because, again, the absolute value. I'm forcing all the charges to be positive, because I like that. I like it that way. And then divide it by the distance squared. The distance is not 10 centimeters. These are 0.1 meters. Gotta convert to meters. So divide it by 0.1. That's squared. You plug this all in your calculator, and you'll get 4.86 times 10 to the negative 5th. But then that begs the question, which direction does this point? And to figure that out, here's what I'm going to tell you. We have 4 directions in physics. We have the positive x-hat direction, which means right. We have the negative x-hat direction, which means left. We have the positive y-hat, which means up. And we have the negative y-hat, which means down. Now, even if your professor doesn't use this as much as I do, I'm going to tell you I will absolutely use x-hat, negative x-hat, y-hat, negative y-hat, because it makes perfect sense. It's saying what direction, and you cannot mix x and y's. Okay? If you want to mix x and y's, you got to do Pythagorean theorem, which isn't fun, but sometimes we have to. So anyways, I have to think about this. Does this point to the right or the left? Well, for these charges, the 2 on the left, obviously they're opposite charges, which means opposites attract, and it actually will point to the right. And since it points to the right, that means I'm going to say positive x-hat. Any questions there? No? Okay, good. So then now we will continue with the other 2 charges. Remember, the other 2 is not the 9 and the 30. As a matter of fact, I don't even care about the 9 and the 30. I only care about the ones acting on the 6. So next I'm going to do 6 and 30 nanocoulombs. That force is going to be K, 9 times 10 to the 9th, times numerator, 6 times 10 to the negative 9, times 30 times 10 to the negative 9, divided by the distance squared. And once again, the distance is 0.1, right? Wrong. The distance is not 0.1. It's the distance from here to here. So in other words, double it, 0.2. So that's 0.2 squared. I gotcha. Can never trust a tutor. And luckily I plugged this in my calculator earlier today. And I got 4.05 times 10 to the negative fifth power. And again, I got to figure out if this is x hat or y hat or maybe negative x hat or something. So here's what we're going to say. These two positive charges, they're obviously both positive. In other words, they're going to repel each other, so they go like this. So in other words, that force points to the left, and that's going to be the negative x hat. By the way, instead of writing negative x hat, you can say the whole number is negative. That's what I'm going to do. If you have negative x hat, the whole number is negative. And then I just put, regular x hat, because I already used the negative. I moved it out in front. And then if I want my final answer, then all I'm going to do is I'm going to take the two answers I just got, 4.86 times 10 to the negative fifth, minus 4.05 times 10 to the negative fifth, and I plug that in the calculator, and that will give me 8.1 times 10 to the negative 6. Units are newtons, and since the answer is positive, it points to the right. If I got a negative answer, it would point to the left. Any questions on number 12? No? Okay, good. Next, number 13. When two charges, positive Q and negative Q, are placed a distance d away from each other, the electric force between them is F0. If you double the charge on both and triple the distance between them, what is the new force in terms of F0? I'm sure you guys love problems like these. I know I do. And so what I'm going to do is basically treat it like the intensity problem we did earlier, where the car was honking 100 feet away and then 300 feet away. It's very similar to that. So first I'm going to say F0, the original force, is equal to K, and I'm not plugging in numbers because you see all these variables. Like, there's no reason to plug in numbers if everything else is in variables. A lot of it's probably going to cancel. So K times positive Q times, well, I guess negative Q, but since I use absolute values anyway, it's just going to be Q. And then divided by the distance, which they say is d squared. Obviously, I don't know any numbers. If they gave me numbers, then maybe I'd write them, but it doesn't matter. And now for the new force, which I'll call F new. For the new force, K doesn't change. Both charges doubled, so now it's 2Q times 2Q. And then divided by the new distance. The new distance is 3d, and that whole thing is squared. And now the question is, how does this simplify? I'll show you. So for the numerator, 2 times 2 is 4. You get 4q. That's 4q squared, because q times q is q squared. You could even say the same thing for the original one. Like, this is k, q squared over d squared. You can say that too. And then in the denominator, I have to square both the 3 and the d, so it's 9d squared. And now I just have to compare these two answers. Once again, k q squared over d squared shows up here and here, and the only thing that's left over is the 4/9. In other words, the answer is 4/9 times the original F0. I'll write it over here. 4/9 times F0. That is our answer. Because those were the coefficients that were left over, so that means that must be the factor we multiply by. And whenever you see a comparison problem like this, don't get freaked out. Just do it the same way I did. What did I do? I wrote up the original one, and then just wrote the new one, and asked myself what changed, and compared my answers. It's really not that bad. Okay, I'm not gonna lie. Number 14, I made like way too hard, and I didn't think it would be this hard, so I apologize in advance. But here we go. Number 14. Two charges lie on the number line as shown. Where should a third charge minus 2q be placed so that the net force on the negative 2q charge is 0? So as you can tell, there's no negative 2q charge anywhere here. We're going to add it. And this would be a separate question I am going to ask you, the audience. I want to know, will the negative 2q, will it go on the left side? Will it go in the middle? Or will it go on the right side? Who thinks they know where it will go? Yeah, so this is a tough one. I know you're thinking about it. You're probably stuck. Let's just guess. You know, there's nothing wrong with guessing. We'll figure out pretty quick if we're right or wrong. Let's guess the middle, because that makes the most sense, right? So if I put it in the middle, that's a negative charge, right? So negative 2q. Think about it like this. The negative charge, in other words, my black dot and the blue dot, those are going to be repelled. So it's going to feel a force to the left, like that. I know it's hard to see, but that is one arrow to the left. Then the red one. The red one, that's an opposite charge, right? Opposite charges attract. So you're going to have another arrow to the left. And because you have two arrows to the left, you will never, ever get a net force of 0. So for that reason, it cannot be in the middle because both charges make it want to go to the left. So it's not in the middle. That means it's either on the left side or the right side. We've basically doubled our chances of getting the right answer. So who thinks they know left side versus right side? This is easier. Man, not even a guess? I'm worried for you guys. But I'll say this. This is like a tug of war game. What do I mean by that? I say it's a tug of war game because you need the net force to be 0. And who right now is stronger? Obviously, it's the 16q, right? So this guy's stronger. And so for that reason, many people put the charge on the left side, and that doesn't make any sense. Then the 16q is just going to win, like outright. But there's more than just strength, like charge, when it comes to balancing out forces. Distance also matters, because distance shows up in that force equation. And I think we all know, if you're closer to the charge, that's going to make it stronger too. So even though the 16q can be stronger, if we put it closer to the minus q, that's going to balance out the charges. So I don't know where it is exactly. I'm just going to put it here for now, but I know it has to be on the right side. Left side is wrong. I'm going to erase some of this to clear up some space, but you can leave it, obviously. So I'm saying it has to go on the right side. This could have been a question just on its own. But now I actually got to solve it. And for that, again, I'm going to define some variables. Let's say this distance right here, I'm going to call x. And yeah, I'm just solving for x again. Okay, so here we go. If we want to find the net force here, this is charge negative 2q. What I got to do is, first I'm going to find the force between negative 2q and negative q, the two close charges. I know that force is going to be k, which is 9 times 10 to the 9th, times both charges. Obviously, I don't know what the charges are, so it must not matter. But q times 2q, again, I'm taking absolute value because I don't care about the sign. And then divided by the distance. The distance between them is x, it's my variable, so x squared. Any questions so far? Oh, and if I want to find the direction for this, then what I would say is, well, negative charges repel, so it must be pointing to the right. So that is the right, which is x hat, positive x hat, it points to the right. And now I'm going to do the same thing, but for negative 2q and positive 16q. Negative 2q and positive 16q. This one's harder. So the electric force is equal to, again, 9 times 10 to the 9th, times the two charges, so 2q times 16q, taking the absolute value. And then who knows what this distance is in terms of x? So between 4 and 7, that's a distance of 3. So then the total distance is 3 plus x. 3 plus x, quantity squared. There we go. And now, since I want a net force of 0, also I forgot to mention, these are opposite charges, negative 2q and positive 16q, so that will point to the left. In other words, negative x hat. And this is great because now I have a chance of getting 0 net force because one points to the right, one points to the left. And since they're equal to each other, I can just set them equal to each other. I don't even have to worry about the negative sign. The negative sign really doesn't matter if I just set them equal to each other. Okay, so in other words, 9 times 10 to the 9th times 2q times q is 2q squared. I guess I don't need parentheses. Divided by x squared. Remember, this was the first force. Then the second one we just found, that's going to be 9 times 10 to the 9th. Numerator is 32q squared divided by 3 plus x quantity squared. So this is the setup for the equation. The hard part's done. Now that's left is the algebra, which of course is the other hard part, especially for this problem. Good news is that 9 times 10 to the 9th canceled and q squared canceled. If you want, you can even reduce the 2 and the 32 because that reduces to 1 and that reduces to 16. And then the x's do not cancel. If you do, you get the wrong answer, so I don't recommend doing that. So then what I'm left with is, on the left side I have 1 over x squared, and on the right side I have 16 over 3 plus x quantity squared. And so now it's just a matter of solving. I'm going to cross multiply these. So on the left I get 3 plus x quantity squared equals 16x squared. This is great. Now I just got to FOIL the 3 plus x. In other words, write it out like this. And then I got to FOIL. I'll get 9 plus 6x plus x squared equals 16x squared. And now I got to solve for x. So minus x squared from both sides, and I will get, well actually I'm going to subtract everything. Minus 6x minus 9. I'm going to have it set equal to 0. So 0 equals 15x squared minus 6x minus 9. And I forget if this factor is nice or not, but either way, I did quadratic formula for us already, which I'll write down just so you have it in your notes. The quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. God forbid you need that on the test, but in case you do, here it is, so don't freak out. I bet they'd give it to you on an equation sheet, however, as most things, I recommend memorizing it, honestly. So then finally, after you do quadratic formula, again, I did this earlier, you get two answers. One answer is 1.6, and the other answer is negative 0.4. Negative 0.4. So obviously we can't have a negative answer here. That would not make any sense. It looks like the answer must be 1.6. And the reason I'm not circling that is because the question asked, where should it be placed? In other words, where should it be placed? Well, we said x was the distance away from 7. In other words, the final answer is 7 plus 1.6, which gives us 8.6. And that is where you put it. You put it at 8.6 on the number line. Any questions? Nope. Okay, good. Now we're just going to continue. The next couple will be pretty quick. We did most of the intense math already today, so that's good. Even though we're on question 15, we're more than halfway over. So, number 15. Below is the electric field line diagram for 3 charges. The charges have not been labeled. You'll notice that if you printed out this earlier today, I messed up this question. I changed this charge to a positive 3 charge. That's not to say that that's the answer. I'm just saying put positive 3 if you printed this out. Or if you're following along on the PDF that I sent you, that's wrong too. This needs to be positive 3 in order for the answer to make sense. Okay. So, which of the following are possible values for the charges from left to right? All you need to do for this question is to remember that it needs to point away from positive and toward negative. And because of that, we can safely say that the left one must be positive, the middle one must be negative because the lines are going towards it, and the right one must be positive. And so the only answer choice that has positive, negative, positive is literally A. And yeah, that's why I messed up. There was no right answer when I originally made it, and I was like, that's not good. So any questions there? Oh, here's a good question for you. Do the numbers matter? And the answer is not really. What matters way more is the positive and negative charge. Okay. Next, number 16. You have a positive charge on the positive x-axis, a negative charge on the positive y-axis, and a positive charge on the negative x-axis. If all the charges have the same magnitude, what is the direction of the net electric field at the origin? So I would let you do this one on your own if it weren't for the fact that this is the first net electric field problem we're doing tonight. And so I'm going to take care of it. A lot of you are happy because this is bonkers confusing. But for those of you who want to try it on your own, I guess you can still try it while I'm talking, but whatever. So I have a positive charge on the positive x-axis. So I'll just draw that right here. This is positive. I have a negative charge on the positive y-axis. That's like somewhere over here. And that's a negative charge, so minus. And then I have a positive charge on the negative x-axis, so somewhere over here. And that's a positive charge. And then I want to know, if they all have the same magnitude, what is the direction of the net electric field at the origin in the middle? So to figure this one out, here's what you need to do. I have 3 charges that I need to consider for their directions. So we'll deal with this one first. Since it's a positive charge, the electric field lines point away from it in every direction. But since I'm only looking at the origin, there's only one arrow I care about, and it's the one pointing to the left. It's the only arrow I care about, and that's how I want you to draw your electric field lines on questions like this. Just the one between the point we're looking at and your charge. So for the same reason, when I look at that negative charge here above, negative charges point towards the negative charge. So it's going to point from the origin to the negative charge. Hopefully that makes sense. Any questions so far? Okay, good. And then the last charge, it's another positive charge. So I'm going to be drawing it away from the positive charge towards the origin. And that's supposed to be like this, the same length as the other arrows because they all have the same magnitude. So there, that's better. And now if I want to find the direction of the net electric field, I have to add these 3 vectors together. Hopefully you realize that 2 of them will cancel, the green and the red. They have the same magnitude but point in the opposite direction. So then the only answer left is the blue arrow, which points up. And so that's why answer choice A is correct, up. Any questions on that one? Yeah, I know that one's tough, but hopefully that makes sense. Because we have 2 more, just like number 16, right now. So for number 17, I want you to try this one on your own. What is the direction of the net electric field at point P? I'm going to give you a minute to do this, but we're going to do the same strategy we just did for the last one. So go ahead. Okay, I'm going to say time's up. I also just realized this question jumps from 17 to 12 in the next one, so I really messed up with the numbering here. So who knows how many questions are in this review. Anyways, if you want to find the direction of the net electric field, all you gotta do is draw 1 arrow away from the positive charge and 1 arrow towards the negative charge. I do not care about the arrow between these 2 because I only care about point P. So if you did draw that, that's wrong. So now if you want the final answer, I just gotta draw the 2 arrows next to each other, connecting them tip to tail just like we would in Physics 1. And then the end result is going to be the starting point to your ending point. And it's just this black arrow here that connects the 2. So in other words, the final answer is to the right, straight to the right. Answer choice C. Any questions? No? Okay, hopefully that made sense. And then the next one, which again, crazy numbers, but number 12, we're going to do the exact same thing for this one. So again, I'll give you a minute, try it on your own first. And tell me, but don't tell me what you get, just be quiet when you're done, which I don't think I have to tell you twice with this group. Okay, so I'm going to say time's up for this one. Hopefully you got it. Once again, I just draw an arrow away from the positive towards my point P. Top right, same thing, down and to the left. For the third charge, still positive, so still away. And the only one that points towards is the very last one, negative Q. That's going to point down to the right. So for this one, you can either add the 4 colors up, which you can do, or you can recognize that the blue and the green will cancel. Those 2 diagonals cancel. And so the final answer is just an arrow that points down to the right and then keeps going down and to the right. In other words, the final answer is just one big arrow that points down to the right. Any questions on that one? No? Okay, hopefully the direction of the electric field stuff makes sense now. And with that, we have number 13. Number 13, I don't think you will get right, no offense, but I'm going to ask it anyway. An electron passes through the electric field as shown. Which direction will the electron travel? To answer this question, you need to remember how charges interact with electric fields. And what do I mean by that? Remember, this was like one of the first things we said about electric fields, and that the field lines show, so I'm going to write this down, field lines show where a proton would go. The field lines show where a proton, or just a positive charge in general, would go. So in other words, if this was a proton, the charge would want to go this way. It would be making a right turn, basically. But since it's a negative charge, it's doing the opposite. It's going to go this way. And notice it's a gradual shift. It's not a sudden left turn, okay? Just like a car making a turn, it's gradual. And that's it. That's the answer. It just goes up because electrons do the opposite. Electrons go the opposite way. So very easy. Nope. Okay, then we're on to number 14. A positive, this question's fun. A positive charge is suspended in midair. To counteract the force of gravity on that charge, which way must the electric field point? And then the second question, if the electric field is created by a negative charge, where must the negative charge be placed in relation to the positive charge? A lot of you saw a question like this on the homework, and it's definitely a Physics 1 kind of question. It combines Physics 1 and Physics 2, because it's forces and it's electric fields. So here's what I'm going to do. First, I have my positive charge. It's hanging out here. It's got a mass of mg, and I don't have any numbers here, so I'm not asking for you to solve this question with numbers. I just want to know which way the electric field would point to make this thing suspended in midair. In other words, if it's suspended in midair, the net force is 0. In other words, I think you know this, but there must be an electric force pointing up. So the question is, which way will the electric field point to make the force go up? And so what most people say for this problem, and wrong, but most people say, oh, it's a positive charge, the electric field points away everywhere. Don't write this is wrong, just observe. The reason why this is wrong is because the proton, yes, it's giving off this electric field, but it can't push itself. In other words, if we want this proton to go up, you cannot count its own electric field. It would be like trying to pick yourself up. Like literally, this is the analogy I always use. It's not a great analogy, but I like it. Imagine you want to literally pick yourself up. In other words, you put your hands under your feet and you start lifting as hard as you can. Are you going to start floating up in the air? No, of course not. If you try and you do it, let me know. You're a superhero. But it's not going to happen. If you try and pick yourself up by literally lifting yourself up, you're not going to do it. Same thing here. The electric force from the proton is not going to make it go up. It kind of ignores it. So let me erase these lines. They're all wrong. What I'm saying is there is an external electric force. There's an electric field. There is an external electric field that's causing an electric force pointing upwards. And that field can either point up, down, left, right, even a diagonal. But I think the only two logical answers, it either points up or it points down. And to answer the question of whether the electric field points up or down, I remind you that electric field, obviously it points away from positive and towards negative. We said that already. But it also points in the direction that the proton would want to go. Which way does the proton want to go? Proton wants an electric force up. That's what the little Fe is. The proton wants an electric force up. That means the electric field must point up. E points up. Done. A lot of people have trouble with that. And by the way, if it was an electron, it would be the exact opposite. The field would point down. So I know this is confusing to a lot of my students, but maybe I explained it better this time. Does anyone have any questions? Okay. There is a second part to this question. If the electric field is created by a negative charge, where must the negative charge be placed in relation to the positive charge? There's two ways you can think of this. I would also say there's only two logical answers. You're either going to put the negative charge below or you're going to put the negative charge above. Doesn't make sense for left or right side. So if you say above, let's just say that you said above, remember that electric field lines point towards negative charges. In other words, your arrow would point that way, and frankly, I think that's perfectly right because your electric field points up. So up is perfect. If you pointed it down, I mean, obviously it looks like you have this arrow here pointing down, but remember, that's mg. That's not the electric force. So the negative charge cannot be below, it has to be above. And then the other way you could have thought of this is that opposite charges attract to one another, and an attraction force will push the positive charge upward. So no matter what way you think of it, the negative charge must be above. That's the answer. Any questions? No? So if that's the case, then we're going to take a 5-minute break, and then when we come back, we will be discussing Gauss's law. If you do have any questions, I'm going to stick around so you can ask them, or if you need me to go back up and I'll show you whatever. But we'll meet back in 5 minutes, 8:55. I'll get started right at 8:55. Okay, let's get back to it. By the way, during the break, I counted how many questions there actually are, because I'm curious. The actual number is I think it's over 34, but since we skipped the last few questions, we're only going to be doing 30 from this packet, and then I have an extra 2 that we're going to look at, so a total of 32, which is more than I normally do, but at the same time, we have so many conceptual questions that go by a lot faster. We should be done definitely before 10 o'clock. So, next we have Gauss's law. And what better way to start talking about Gauss's law than electric flux, which is what Gauss's law uses. It uses electric flux. So here's the equation. Electric flux, which has this symbol, phi, is equal to E, the electric field, times A, the area, times cosine theta. Now, cosine theta is pretty obvious when it shows up. In other words, you'll clearly see an angle in the problem. If I don't give you an angle, you should not use cosine theta. It would not make any sense. But the best way I can describe electric flux is imagine you have a butterfly net and you try and catch all the electric field you can with that butterfly net. And your butterfly net has area A, and your electric field or your butterflies have magnitude E. And what Gauss's law says, well, basically electric flux on its own is pretty useless to us. But then Gauss came along, and yes, of course, this is the same Gauss for mathematics, used in Gauss-Jordan elimination method for solving matrices, but you guys clearly don't know that. Either way, Gauss's law says that the flux is equal to E times A, which is also equal to Q enclosed over epsilon naught. Now this thing, Q enclosed, that is the charge inside. Inside what? Inside your Gaussian surface, inside your butterfly net. And then epsilon naught, this is another constant. This one's 8.85 times 10 to the minus 12th. That's what epsilon naught is. It's going to be given to you on an equation list. You'll also notice that I left out the cosine theta. Why? Because when we use Gauss's law, you are not going to need cosine theta. If you do, something went horribly wrong. So basically, you use Gauss's law when picking a surface that you don't have to worry about the angle. If you do have to worry about the angle, it's not Gauss's law, it's just electric flux. Okay? Any questions with the equation? Okay? And then we have surface charge density, which has this symbol. It's lowercase sigma, the same symbol used for standard deviation in statistics, fun fact. And that doesn't have anything to do with physics, though. So sigma equals charge Q over area A. It's just a charge over an area. And the area that we use, like every time, well, not every time, but the most common area we use is the surface area for a sphere. Surface area for a sphere. Which we actually mentioned earlier today when we talked about the intensity equation. It's 4 pi r squared. So if you're going to memorize any area formulas, you should memorize this one because it shows up twice in 2 different topics. But you don't always need that equation. You don't always need that variable. So let's look at some problems and let's get a feel for it. Number 15. What is the electric flux for each of the 3 Gaussian surfaces? Each charge represents plus or minus 1 Q. Write your answer in terms of Q and epsilon naught. So this is Gauss's law. We have these Gaussian surfaces and we need the electric flux. Remember, there's 2 possible equations you can use. One is E times A. The other is charge enclosed over epsilon naught. We don't need both for this problem. And if you use the first one, electric field times area, I would ask you, what's the electric field? And you'd say, I don't know. And then I'd ask you, what's the area? And you'd say, I don't know that either. So if you choose that, good luck. I'm not going to help you. Instead, we're going to use the charge enclosed. This is the charge inside. So if I start with surface A, then flux A is the charge inside, which is, that's each one's Q. So minus Q plus Q. In other words, minus 2Q plus 1Q over epsilon naught. That's going to give me a final answer of negative Q over epsilon naught. And I'm not plugging in any numbers because look at what it says right here. Write your answer in terms of Q and epsilon naught. So this is it. Just add the charges, divide by epsilon naught. Any questions? Okay, then I'm going to give you a minute to find B and C on your own. C is the trickier one. Okay, I'm going to say time's up. So for B, pretty easy. There's only one charge inside. So flux B must just equal positive Q over epsilon naught, and that's it. And then for C, if you only look at this charge for C, you're wrong, because you need to consider all of the charges. 1, 2, 3, 4, 5. And so for C, it's going to be flux C equals the total charge, that's negative 3q plus 2q, because there's 3 negative charges and 2 positive, divided by epsilon naught, you'll get a final answer of negative q over epsilon naught, and that's for surface C. Any questions? Now, by the way, if a question ever comes up about Gaussian surfaces are not real. Like, they're imaginary. You get to define them like an imaginary box that you draw out in space. But they don't actually exist. So if there's ever a question about that, they're not real. You just make them up. Okay, next, number 16. A metal spherical shell has a radius of 8 centimeters and a surface density per area of negative 16 microcoulombs per meter squared. Hopefully you realize that this thing is the surface charge density, that it's sigma, and sigma is negative 16 micro. Micro means 10 to the minus 6. Okay, let's continue. How much charge does the shell have? So it looks like we're solving for charge this time. To do that, I'm probably going to start with the surface density per area, or surface charge density equation, because I don't even think I need Gauss's law right now. That density is equal to charge Q over area A. Since I said it's a spherical shell, that means that A is going to be 4 pi r squared, like I said it usually is. So now, sigma is going to equal negative 16 times 10 to the minus 6 equals charge Q, which is what I'm solving for. I want to know how much charge. And then divided by 4 pi. Radius is 8 centimeters. Please don't use 8. It's 0.08. You got to divide by 100. And then we square that. So if you want to solve for Q, just multiply the denominator on both sides and just plug it in your calculator. You'll get Q equals negative 1.29 times 10 to the minus 6. This is coulombs. Or if you want to convert to microcoulombs, because 10 to the minus 6, that's microcoulombs, you could also say negative 1.29 microcoulombs. Both answers are correct. I recommend knowing how to convert between the two, especially for a problem like this, where you get the answer is 10 to the minus 6. So very handy to know that. Any questions? Nope. Okay. Next we have number 17. 17, basically I need to give you an equation that I honestly don't know if they'll give it to you or not, but it's been on exams in years past, so let's do number 17 and then I'll explain. 4 very large plates are lined up side by side. Each plate has a surface charge density of sigma. What is the magnitude of the electric field in the space between the two leftmost plates? Express your answer in terms of sigma and epsilon naught. So this question's almost unfair. I say almost unfair because if it does show up, then if you don't have this memorized, you have no hope of getting the question right. So these are infinitely large plates. Why are they infinitely large? Because I said so. The question says very large plates, and as far as we're concerned, these are infinitely large. If that is the case, the electric field for infinitely large plates is sigma over 2 epsilon naught. If you do not have this memorized, and you see a question like this on the test, you're just screwed. Okay, there's nothing you can do. You're supposed to derive this using Gauss's law, and you're supposed to derive it using not a sphere. You're supposed to use a cylinder, and it comes out of like both sides for the electric field. And I have a video explaining it on YouTube, and it's just so complicated and convoluted. It would take like 30 minutes to explain it right now. And so for that reason, I'm not going to do that, obviously. Instead, I just tell you to memorize this, because if it shows up, you'll know what to do. And a question like this is very common, okay? So this is the formula you should memorize. I boxed it. And now we want to find the net electric field between these two leftmost plates. In other words, the electric field in this area right here in red. And here's how we're going to do it. If you remember that electric field points away from positive charges, and even though it doesn't say it's a positive charge, we can just assume the plates are positive charge. because it's fine. You can assume it's positive. Then that means that the electric field is going to point away from these plates in both directions. And you'll notice I did it for all four. Okay? Now, the thing is, it looks right now that the net electric field is 0 because one arrow points to the right, one points to the left. But one thing that you did not know about these plates is that they can pass through each other. In other words, when I draw the arrows for the third one, for instance, I can really draw them going all the way to the left and all the way to the right. Similar for the fourth one, I can draw them going all the way to the left and all the way to the right. And that's just because how these electric fields work. They can pass through other fields. But then you're thinking, but they got to be weaker, right? Like the electric field can't be just as strong. Like, just think of it logically. If I put a dot right here, and I put a dot like way over here, you can't tell me that this distance doesn't matter for the distance and the effect of the electric field. And the thing is, that's exactly what I'm saying. The electric field is just as strong, but only if your plate is infinitely large, which is impossible in real life, but possible in physics problems like this. So what am I trying to say? I'm trying to tell you that the electric field is 1 positive E, in other words, 1 E to the right, minus 3 E to the left, because I have 1, 2, 3 arrows pointing left. The net result is negative 2 E, and remember each E is sigma over 2 epsilon naught. So in other words, the answer is negative 2 sigma over 2 epsilon naught. The 2's cancel. You get negative sigma over epsilon naught. And since the question clearly says magnitude right here, magnitude means make your answer positive. I don't want the negative. So the final answer is sigma over epsilon naught. And I know that's confusing, but hopefully that made sense. And if not, you can just rewatch the video later, and it'll probably make even more sense then. So any questions on that one?
So we know to use this equation just when it says something about large plates.
Yes, that's exactly right.
Okay.
Hopefully it doesn't even show up. I don't know if it will. It has in the past. So if you get it wrong, it's not my fault. And if you do get it wrong, or I guess if you don't get it wrong, then it's if you get it wrong, it's not my fault. But if you get it right, then you should be praising me. Anyways, number 18. A spherical conducting shell has plus 3 coulombs charge in the center. The conducting shell has a net charge of negative 2 coulombs. What is the charge on the inner and outer walls of the shell? So the first thing you need to know about the spherical shell is that it's hollow in the middle. Like you see the gray? The gray is the shell, and the middle is empty space, except for this plus 3 coulomb charge in the very center. Now, we want to find the charge on the inner wall, which I'll call Q inner, and we want to find the charge on the outer wall, Q outer. And you may be thinking, are they really different? And the answer is yes, they are very different. Okay? So here's what I'm going to do. It actually is going to use Gauss's law. And how do I know that? Because as soon as I see the word spherical conducting shell, I immediately know to use Gauss's law. It's like I've just done this so many times. As soon as I see those words, spherical conducting shell, or just like a sphere in general, or you put a charge in the middle, it's always Gauss's law. I just know that. Now you do. But the question is, where do you put your Gaussian surface? And the answer is, I put it literally inside the middle of the shell in this little space right here in between the inner and outer walls. Now, why on earth would I put it there? It's because I actually know where the electric field is there. This is something else you probably didn't learn in class. I know I didn't tell any of my students this because we just never got this far. But the electric field inside a metal is always 0. And that has to do with the fact that electrons are like an electron soup. in metals, and that's more of like a chemistry explanation, and I don't have a good physics explanation, but I know the electric field is always 0 inside a metal. And why is that good? Well, because think about it. If I use Gauss's law, and Gauss's law says this, EA equals charge enclosed over epsilon naught, and I just told you the electric field 0, oh my god, this is great. It means that the charge enclosed must be 0. That's the only way this math adds up. Now, as you know, the charge in the middle is 3 coulombs. That's not 0. Can someone help me make sense of this? It's because the Q on the inner wall balances it out to 0. Let me explain. You have 3 coulombs in the middle, but the entire thing enclosed needs to add up to 0. So what I'm saying is 3 coulombs plus Q inner must equal 0. Why must it equal 0? Because of Gauss's law. Okay, Q enclosed must be 0. So 3 plus Q inner equals 0. Subtract 3 from both sides. The inner wall is negative 3 coulombs. Now let's think of it from a logic perspective. We just proved it using Gauss's law. From a logic perspective, this makes sense. The metal wants to arrange its negative charges so that it's exactly negative 3 coulombs on the outer wall, spread out evenly, so that way it perfectly balances out the 3 coulombs in the middle. That makes sense. But then the question still remains, what's the outer wall? So first let me circle this answer. We got our Q inner. And to find Q outer, all you have to do is remember that what's the total charge on the shell? It says in the problem, the conducting shell has a net charge of negative 2. So in other words, if we'll say Q total is equal to Q outer plus Q inner, and we just said the total is negative 2, Q outer is what we still need to solve, and we just said Q inner is negative 3. Whoops, too many equal signs. Negative 3. I add 3 to both sides, and it looks like Q outer must be positive 1 coulomb. In other words, you don't even need Gauss's law for that one. You can just use conservation of charge. Any questions there? That was a tough one, so assuming everyone's good, we will move on. The next topic we have is the second to last topic of the night, electric potential and electric potential energy. So this is going to round out our 4 equations, and I say 4 equations because the first one was electric force, the second was electric field, the third is electric potential, which is also known as voltage. I'll write that right here. And then the fourth and final equation is electric potential energy. So electric potential has a simple equation, V equals KQ over D. You'll notice 2 things are missing. Number 1, it's not squared, it's just D in the denominator. But perhaps the bigger thing that you notice is there's no absolute value signs. As a matter of fact, there's no absolute value for any of these, electric potential or electric potential energy. And that's because the sign does matter. Okay, it matters. If you remember, we put absolute values for forces and fields because we find the direction by hand. We don't do that with electric potential. If you have a negative charge, it's a negative voltage. Simple as that. And then for electric potential energy, I have the equation U, which stands for energy for some reason, is equal to K Q1 Q2 over the distance, not squared. And again, no absolute value. And by the way, we do have 2 more equations that I need to show you right now that are going to relate electric potential and electric fields and a bunch of other stuff. The next equation I want to write is delta V equals negative E times D. And if you've met with me before, you know I ignore that negative sign because once again, I figure out the direction by hand, so I don't need it. If you want it and that makes sense to you, the negative sign, then be my guest. I think it confuses me, so I ignore it. The other equation I need to give you, this is another one that has to do with energy. Change in energy equals work. This is from Physics 1. Change in energy equals work. And because of that, or maybe not because of that, but we have a cool equation. The work or the change in energy, whatever you want to call it, is equal to the change in voltage times the charge. And by the way, this one has a weird convention for the positive and negative. I'm talking only about the work for this part. Your answer is going to be positive if we go, I don't want to say we go, if the charge goes the opposite of what we expect. So work is positive if the charge goes the opposite way of what we expect. And I'll explain that in a minute. Okay, I'm assuming you're done writing. So here's what I'm saying. I'm saying if, let's say, I have a positive charge here and I have another positive charge over here, and I force, by taking my hand and forcibly moving the charges closer together, that work is going to be positive because we don't expect it to go that way. But if I move the positive charge that way, the charge is going to be like, I was going to go that way anyway. I didn't need you. So the work is negative for that reason. Any questions? Okay, great. So then just a couple more problems. Number 20, or I don't know what actual number it is, but number 19 is not that bad. Number 20 is probably the worst problem in this packet. And that's okay, because I'm here. Anyways, number 19. A negative 10 volt metal plate is next to a positive 10 volt plate. The plates are 4 millimeters apart from each other. What is the electric field between the plates and which way does it point? Okay, so first I'm going to draw the plates. Don't get confused with what we said earlier with the infinitely large plate. We only do that if they give us a surface charge density, which we don't have. And you would also never use that equation if you have a voltage. Why not? Because when we have a voltage, you better be using this equation. Delta V equals E times D. And again, I ignore the negative sign because I already know which way electric field's going to point. Electric field points away from positive towards negative. So anyways, the first plate's negative 10 volts, this plate's 10 volts, and it's separated a distance of 4 millimeters. I am not going to write 4 millimeters. I'm going to write 0.004 meters. So it looks like I have the distance, pretty easy. Can someone tell me what delta V is? Here's what I'll tell you it's not. A lot of people say 10. It's not 10. Because remember, delta V is V final minus V initial. If we define this one as the final and the left one as the initial, I mean, it really doesn't matter which one you call initial and final, but either way, if you say final is the 10 minus negative 10, you actually get delta V is 20. 10 plus 10, 20. That equals the electric field, which we're solving for, times the distance, 0.004. And all you got to do is divide both sides by 0.004, and you'll get an electric field of 5,000 newtons per coulomb. That's pretty big, but not the biggest electric field I've ever seen. And now what I need to do is, I need to say, okay, well, which way does this electric field point? And forget about the initial and the final. That doesn't matter. What matters is the voltage. One voltage is positive, one voltage is negative. It's going to go that way. It always goes towards the negative, away from positive. And by the way, even if both these answers were positive, in other words, if this was, let's say, 100 volts and this was 110 volts, it still points to the left because 100 is less than 110. Hopefully that makes sense. Any questions? So I'm saying the electric field points to the left. Okay. Next is number 20. Last year, the professor, which ironically it was Ilya, so I don't know why he's not doing it this year, gave practice exams. And this was one of the questions on those practice exams. So, since it's the same professor, I thought it'd be a smart idea to put it on my test, since you guys don't have a practice exam. Why would you? That would mean you're learning and have a chance to prepare for the exam. And we can't have that. No, we cannot. So anyways, with number 20, in the figure below, find the magnitude of the electric field and state the direction with an arrow. The direction's the easy part. The number is the hardest question all of tonight. And that's because even though the equation is simple, you have voltage and electric field, so it makes common sense to use this equation, delta V equals E times D. But the tough thing is, first of all, there's 4 delta V's you could use. And second, you don't know the distance, okay? Because the distance is not this distance here, and it's not this distance here. It's like this distance along a diagonal, and maybe you think you get it, but you probably don't. So I'm going to probably give you the biggest hint. And the biggest hint for this problem is we are going to make a right triangle, which maybe that's what you were thinking after you saw me drawing this. So you have to be careful where you draw this. There's a few correct answers. In other words, there's not just one answer. But what I'm going to choose is I'm going to choose between 10 and 15 volts. And I'm going to choose this distance here, this distance here, and then this hypotenuse, I guess. Now, for this right triangle, I'm going to just zoom in because like it's way too small. Let me just make it bigger, okay? Whoops. So here's a bigger version of what I just drew a minute ago. Now, this side length on the left, hopefully you realize that's just 2, because 2 to 4 is 2. And now the x distance, if I count it, it's 1, 2, 3. So it's 3 for the bottom line. Does everyone see that? It's fine if you don't. Just tell me so I can explain it. Okay. And now, I mean, in terms of right triangles, this is a right triangle, this is a right triangle, but I need to find the red line, and right now I can't find it because I don't have an angle. The good news is I can find this angle here, theta, if I ignore the red line just for a minute and just have 2 up, 3 over, an angle theta, and this is my right triangle. And yeah, I know this is very difficult, but just hear me out. The tangent of theta equals 2/3 because it's opposite over adjacent. And then if you want to find theta, theta is going to be the arctangent of 2/3. And luckily we have our calculator, so I get theta equals 33.7 degrees. And once you know that theta is 33.7 degrees, you can then plug it back in this triangle here. That's 33.7. And now you can just focus on this triangle right here, which I will now zoom in because it's too small. So this is still 3. This is the red distance we're trying to find. I'll call it D. And this we just said was 33.7 degrees. That's the angle. Oh, and this is the right triangle. So in other words, D is not the hypotenuse. It never had to be. It doesn't matter if it's the hypotenuse or not. But 3 is the hypotenuse because it's the opposite of the right angle. So I'm going to say sine of 33.7. And why did I choose sine? I chose sine because the opposite leg is D and the hypotenuse is 3. So multiply both sides by 3 and you get D equals 3 sine of 33.7 degrees. I plugged this in a calculator earlier today and I got D equals 1.66 meters. And once you have the distance, the electric field is not too far off. And that's because we're going to use the same equation we used before. Delta V equals E times D. The delta V, well, I have to go back to my picture real quick. So I'm going from 10 to 15, and I guess technically it matters if I go from 10 minus 15 or 15 minus 10 because it's either positive 5 or negative 5. But notice how I went the magnitude, and the magnitude doesn't care if it's positive or negative. So I'm just going to say positive 5 anyway because 15 minus 10 is positive 5. That equals the electric field times the distance. The distance, we just said it, was 1.66. And so then I divide both sides by 1.66. And I get an electric field of 5 divided by 1.66. And that is about 3.0 newtons per coulomb, which are the units for the electric field. Now we're still going to find the direction, but any questions before we move on to the direction for number 20? Okay. So then for the direction, remember what I said earlier, the electric field will always point away from positive towards negative. Obviously there's no negatives here, but it's going to point towards the lower numbers. It always does. So the electric field will point down and to the left like that. That's the way the electric field points. And now we're done. That was a fun one. And you don't have to agree with that. But are there any questions? Okay, great. Just a few more to go, then we'll be done. Whoops, wrong page. So then for 21, find the total electric potential at point A in the figure below. Write your answer in terms of R, Q, and K. So here's what I'm going to do. I'm asking for electric potential. Remember, that's the voltage. And so I just have to look at one charge at a time. First, I'll look at the positive 6Q. For that, the electric potential or voltage is K, which they want my answer in terms of K, Q, and R, so just K. Q is 6Q, and keep it positive. Do not do absolute value for this one. Do not. And then divided by the distance. This distance is the radius, so it's just divided by R. Great. Done. Next, I'll do negative 4Q. For negative 4Q, V equals, again, K, negative 4Q in the numerator, and the distance is still R because it's still the radius. Okay, good. Now for the last one, it's the hardest one. It's the one at the angle. You got to break it up in X and Y components, or do you? You actually don't. Here's why. For the plus 3Q, voltage equals K times the charge, 3Q, divided by the distance. The distance does not care if you're at an angle. If this was a field problem, electric fields, or if this was forces, then yes, we have to worry about the direction. But we don't have to because electric potential doesn't care. All it cares about is the charge. That's it. Positive or negative, which it was positive. So here's our three answers. And now I just have to add up these three answers together. So it's kind of like basically 6Q minus 4Q plus 3Q. That gives me 5Q as like the total charge. And so then the final answer is V equals K 5Q over R. And that's the total electric potential. Any questions? Great. Okay. Now, the last one we're going to do for tonight from the, at least from this packet, I still have two more to do after this. We're going to skip everything on capacitance after this because you haven't talked about it yet in lecture, and I mean, maybe you talk about it on Thursday, maybe you don't. Even if you talk about it on Thursday, I'm going to put out videos explaining capacitance anyway, so don't worry about that. But number 22, technically number 30. How much work is required to move a 2.1 Coulomb charge through an electric potential difference of 12 volts? This one's actually surprisingly easy, but only if you know the equation that we need to use. Read the question again, and then I want someone to tell me what equation I'm using. No idea? Well, it's the work equation, of course. Work equals delta V times Q. We're solving for work. Delta V says 12 volts right here, so 12. The charge is 2.1. The answer is as simple as 25.2. And that's joules. Now, is that the final answer? Well, I haven't circled it yet, which means it can't be that easy. We just have to figure out if it's positive or negative. Now, this is the hard part. So remember, we need to figure out if it's going the way we expect it to go. This is a positive charge. We expect positive charges to go away from other positive charges and towards negative charges. How do we know what happened? Well, remember, it moved through a potential difference of 12 volts. So in other words, let me just draw two plates again, because I like the plates. And let's say this is 0 volts and this is 12 volts, because that's a difference of 12 volts, right? So here's my positive charge. I'm saying I'm moving it that way. In other words, I'm moving it towards the positive, right? Because if this is like 0 volts, 0 charge, and this is a positive volt, positive charge, I'm moving it the way it doesn't want to go. Positive charge does not want to go that way. And so for that reason, the answer is positive. So positive 25.2 joules. Positive answer. If we were going the other way, it would be a negative answer. Or if we were dealing with an electron, it would be a negative answer. Any questions? No? Okay then. So again, we're not doing this. So then, I don't know where you'll write this. If you have blank paper, great. If not, then whatever. But I just want to talk about one more thing, and that's the electron volt and kinetic energy, and then equipotential surfaces. So the electron volt, here's what you need to know about it. This EV stands for not electric vehicle, but the electron volt, and it is a unit of energy. It's a unit of energy, of all things. So 1 EV is equal to 1.6 times 10 to the minus 19 joules. And I say, hey, where have I seen that number before? Oh yeah, that's the charge of a proton and an electron. So in other words, an electron volt is kind of like the energy for a proton. You can basically think of it like that. And don't forget, kinetic energy equals 1/2 mv squared. I wouldn't be surprised if it shows up on this test. It showed up in a bunch of homework problems. So then here's my question for you guys. How much energy in EV, electron volt, does it take to move a proton through an electric field of 100 newtons per coulomb in 10 micrometers distance? Okay, I'll give you a minute to write this down. Of course, if you're not writing it down, it doesn't really matter. I have the recording, so. But anyways, if I want to find the energy here, here's what I do. First, you can say work, or you can say energy, doesn't matter, is equal to delta V times Q. I have the charge, it's a proton. Q equals 1.6 times 10 to the negative 19. Not bad at all. Delta V is going to be a problem. I don't know it. So I give up. No, I don't do that. We have an equation for delta V. Delta V equals negative E times D, and I ignore that negative sign, because why would I not? And the electric field is 100, and the distance is 10 micro. So delta V is 100 times 10 to the minus 6. This I did not plug in a calculator, so just real quick. 100 times 10 e negative 6. Delta V is 0.001 volts. And now I just have to plug that in the equation. Work equals 0.001 times 1.6 times 10 to the minus 19. I plug this in a calculator. and I get work equals 1.6 times 10 to the negative 22 joules. I don't want joules, I want electron volts. So here's what I do. 1.6 times 10 to the negative 22 joules times, the conversion factor is in the denominator. The denominator gets that number because that's the joules. 1 electron volt goes in the numerator. Joules cancel. That's why I was dividing. So 1.6 times 10 to the negative 19th. Oh, whoops. Did I do that right? No, I have it backwards. 1.6 times 10 to the negative 22nd divided by 1.6 times 10 to the negative 19. I get a final answer of 0.001 electron volts. Well, I shouldn't circle that yet. I haven't figured out if it's positive or negative, but that's the magnitude. So now I'm going to scroll back to the question, and I need someone to tell me if the answer will be positive or negative. Looks like it's a proton moving through an electric field, and I know it's not obvious if we're going in the direction we want to or not, but I'm just going to tell you, if you're a proton and you're moving through a positive electric field, you're moving the way you want to go. Okay? In other words, the answer should be negative. Negative 0.001 electron volts. And that's because the proton's already going the way it wants. And then the last question we have of tonight is for equipotential surfaces. I think you covered this. Maybe you don't remember. But these are the things that look like this. I'm going to draw a series of concentric circles in dotted lines. Kind of looks like an egg. And each of these means something different. For instance, this can be 10 volts, this can be 15 volts, and this can be 20 volts for the outer ring. And what I'm going to do is, I'm going to take a negative charge, right there, negative 3 coulombs, and I'm going to move it all the way around to right there, this spot right here. And all I want to know is how much work. How much work? If you ask me, this is a lot of work. I'm getting tired of this. But the good news is, you'll notice that it seems like I chose a random spot to put the charge. Like, why didn't I just move the charge right there? It's because it doesn't matter. All that matters is the change in voltage, because we know that work equals delta V times Q. And Q is negative 3. And the delta V, let's think about that. Delta V is equal to 20 is the final minus 10 the initial. So 20 minus 10, because final minus initial. I get positive 10. I don't trust my positive or negative answers because I still got to think it through. But right now I'm getting 10 times negative 3. I'm getting negative 30 joules. Before I circle that as my final answer, I just want to think about this. Is this electron going the way it wants to go? Let's see. The electron starts in the middle and then goes out towards the outside. In other words, it's going to a more positive voltage. The electron wants to go this way because it wants to go to a positive voltage. Electron's attracted to positive voltage. So in other words, electron, or just negative charge, it's not an electron, but whatever. Electron goes the way we expect. It's going to a higher voltage. It's going to a more positive charge. So for that reason, we need a negative answer. It looks like this time the signs were right. It is negative 30 joules, but I never trust that based on the work alone. And with that, that's going to do it for this review. I hope all of you are feeling a lot better now. If not, then you just got to do more practice problems. Review your lecture notes, those lecture questions. I mean, I think you can do a lot of them now, I bet. They probably make a lot more sense. And certainly do the homework questions too. Those will always be helpful. And as always, thank you all for joining me in this fantastic review. So have a great night, and please let me know if you have any questions. Bye-bye.